So welcome everyone to the session on intrusion detection systems in critical infrastructure networks. My name is Raik Yakshis and I'm a researcher of the NATO Cybersecurity Center, the technology branch there, and I will host the session today for the next 90 minutes. The security of critical infrastructures is vital and for the well-being of the modern societies. Industrial control systems are used to guarantee and functioning, industrial control systems are used to guarantee the functioning of critical processes and services, but are, however, often outdated and have a lifespan of 20, 30, or even longer, and are not designed to face sophisticated attacks. With the merge of IT and industrial networks, the necessity and the crucial fact that we need to monitor our networks is even more important to identify threats and malicious activities, to strengthen cyber defense capabilities. But before going into further detail, and I will leave this up to our speakers, I would like to introduce our panel. So from the very right from my side, or from left from yours, Mr. Giorgio Sinibaldi. He's an engineer and technology solution manager from Vitro CSAT. He's project coordinator for the FP7 European project Primitive, which is related to cybersecurity for critical infrastructures of utilities. In the center, Dr. Robert Koch. He's a research assistant in the Department of Computer Science at the University of Munich and a member of the University Research Center for Cyber Defense. And last but not least, Trevor Goldman. He is a customer solutions engineer from Waterfall Security Solutions and has over 15 years of experience in cybersecurity field. So thank you, every one of you. You might ask yourself, what are common approaches to identify malicious activities within critical infrastructure networks? And how do those techniques actually work? And how can they be actually improved? And to possibly also improve their results. So your project, Mr. Sinibaldi, deals, or is called Primitive, and it tries to mitigate the security risks of legacy systems. We would like to hear some more about that. So the stage is yours.
Okay, thank you. Good morning. I apologize for my voice, but I come from Italy where now it's 32 degrees, full sun, different weather. So anyway, my project is a project financed by the FP7 European Research Project, which is the ancestor on Horizon 2020. The project we just finished. And it related to critical infrastructures, as Rajek said, especially critical infrastructure on water, gas, and electricity, which are the main utilities all of us are using for our common life. What we have started to deal with this kind of utilities are the threats, which usually are connected with this kind of utilities. We have two different kind of threats, mainly. One is the more, let me say, typical threats, which we are accustomed to, which are communication and software threats, which means denial of service, man of middles, something which we who works in the IT fields is quite accustomed to. But another threats, which is the communication software-related threats. But another threats is very specific of the critical infrastructure, is the process-based attacks. Means you work to destroy the process which makes the utilities give their services. And this kind of attacks, compared with the IT attacks, requires deep knowledge of your process, because each utility has a process of producing, distributing their services. Each one is different from the other. So to be really effective, an attacker needs also knowledge about it. What has been, this is the industrial process behavior attack. What has been done until now is that we have faced the problem with separate view. I mean, we have tools, many tools, which come from the IT field, which have been used to discover attacks on the utilities, and very few tools for the process attacks, I must say. But any of these tools has a separate point of view. I mean, they don't merge their results. They act separately each other. What we tried to do with our project was to merge the information which come from each of these tools separately to make a more deeper inspections of what are the possible threats and to find also hidden threats which can be discovered better if you have a common view of the attacks, not just a separate one. So, as I told you before, our main goal was to provide securities for tools to prevent cyber attacks. And this dual approach is our innovative solutions. This is the slide which displays what's the scope of preemptive. This is a typical SCADA system. You can see this is behind any utilities. You find an architecture like this. And you can see that in these parts, if you see from the top, there is the internet connection, which usually is not something we are involved to with preemptive project. But from the level 4 down, we have the level 4 is usually the control system of the SCADA. And you go down through the various levels of the SCADA system, where you find the final equipment, which may be pumps, valves, everything which is involved with the distribution of water, gas, and utilities. This part from level 4 to level 0 is where the attackers can gain access and where they make damages. What we have tried to do, and now I introduce a slide which gives you an overview of our product or project. If you go down, you see the SCADA system, which is the system I showed you before. Our tools are related each one to a specific component of the SCADA systems. So you find some and each of these tools is a separate one. I mean, we have not an architecture in which we have one global tool which makes everything. Also because this is our consortium of 12 members, it would be too difficult to have one tool with one software to share all together. We have separate tools. Each tool makes its job. So we have the PNIDS tools, which is a tool which makes a deep inspection of the packets which are working on the SCADA system, which is typical Modbus protocols or something like that. We shall have a little detail on it later. We have a tool about the flow needs, means with the traffic which is on the system, on the SCADA system. We have tools which looks at the PLC system, so the host system. We have tools which look at the process of the preemptive, of the system, of the architecture. And each of these tools acts on one aspect of the SCADA system and works independently each other. What gives more, what's the added value of the preemptive system is that all these tools have a common format which has been defined between all the members. All the events, all the alarms which have been found by each of the tools, so each strange behavior which each tool has discovered, is sent to the correlation engine, which is the common database where all these events are collected. So you have some events let's say, highly critical events, which may be discovered by single tools. So maybe that the tool discovers a man-in-the-middle attacks, the packet tools. So this is an alarm which is immediately sent to the operator. But there may be other events which have been discovered by the tools, which in itself are not something which is an alarm. Like for instance, opening a pump which is a common situation, but opening a pump when the pressure is very high means breaking the pipe. So this is something which is maybe correlated between different events, a command to open the valve, the situation of the process, which is a strange state. These two situations in itself are not detected by each tool, because if I open a valve, it's not something which I cannot do if I send this command. But if I take together this situation, these events from different tools, I can have a situation which is a real threat, which could not be discovered by each separate. So what happens in the KA, which is the correlation engine, is that you have the possibility to find threats which are not discovered singularly by each tool. This is the real difference between other aspects, between other tools which we can find on the market. Also, if this is a research project. Okay, I shall not enter in detail about all the tools because it will be too long, obviously. But just to let you understand one tool, which is the packet tools detections, which makes an inspection of the network activities. We make an inspection of variables, which is so made. So in the first step, we choose a series of variables, which are those which are running in the system, the SCADA systems, and we make, by the step 2, an analysis of such a variable to see if this variable is a command, is a set point, or something important. So we learn about this variable, and we make a detection in the prediction of which will be the value, the direct value of each variable. So if a variable is different from what we expect, we launch an alarm. So we launch an alarm on the system, which does not mean that the operator sees an alarm. Because as I told you before, we want to decrease the number of false positives. We just send an alarm. Maybe that the other tools in the same time are sending some alarms, so there may be some problems. Okay, here, for instance, you see what is the main contribution of the packet needs. So we see that this packet works without the prior knowledge of the system. So it detects all the packets, all the variables, and automatically learns which one are the most important. So in theory, it's not important that someone of the process of the real utility gives us support, but this is an important topic. If someone of the utility gives you information, obviously it's much more easier to find variables which are important. Okay, here are the other tools, like for instance the flow needs tools, which makes instead the detections of, for instance, a variation on the traffic. You know that the SCADA system usually have a traffic which is very standard, very common, has always the same nature. If there is a traffic which is anomalous, as a number of packets, this is another alarm. This is just an alarm to say strange. We have instead other, for instance, for the PLC detections, we have a tool which has worked on a specific PLC, a Raspberry PLC, because you know that to make a tool work on a PLC, you have to make an agreement with the builder of the PLC. So we have installed this agent on Raspberry PLC, which are quite common for the home usage. And so on. We have other detection. Another detection which we focus on was the USB detection, because many, like Stuxnet probably, tools systems have been infected by a USB key. So we have also some system to check them. And so, as I told you before, the CAIA, the central engine, where all the alarms are collected, is made to limit the number of false positives, which is the main issue usually in these tools. Or you have too many false positives, or you have not, or if you decrease too much, you have no alarms. The CAIA needs to reduce because it correlates the events, so it tries to reduce them. And just to finish my part is just to talk to you a little bit about the process level, because the process levels, as I told you before, is something which is not usual. Not many tools check the system from the process level. The main idea here is that we use a negative algorithm selections by which we detect the state of a system, and we measure all the state so that the system may be in some specific state in a certain moment, with pumps in a certain level, something like that. So that maybe that we find a situation in which the process of the system is not in the situation in which it should be for that moment. And obviously this is related to the situation. For instance, the power consumptions during the night might be lower than during the day. So we have obviously this kind of configuration. So we have a tool which works, which makes a training phase. So it takes the process data which come from the system, detects all the situation of the components of the systems, and makes a detection of the states. So makes a state which the normal state of the process, which should be normal, and detects when the system finds itself in a normal state. This is made by this one, like you say, the process data, etc. So this defines the operation of at each time of the state of the various variables of the system, which compose the system. We make of these the operational states which are possible for the system. Then we make this diagram, which shows you which are the normal operations. The green one are the normal operations, and the gray one, sorry. The green one are the detectors. So if you find that your system finds itself in a state which is not in the gray situation, it means that your state, your process in that moment is out of the normal operations, which once again in itself may be not meaningful, because it may happen that, for instance, there is a peak in consumptions. But once again, if you see that a normal operation has happened just before a strange packet had been sent on the network, or a PLC has raised an alarm because something has happened, the correlation engines say, okay, I have 3 different situations. I have 3 states which are not normal, so I raise an alarm. Okay, there's a, I think it's just to give you the rough idea of what is available by the preemptive project, what has been, we have studied on it. And I think it's just 20 minutes.
So thank you very much, first of all. Are there any questions to either this? Oh, You are on the next slide. On the last slide or on any other thing? Yes. Yeah, of course.
Thank you very much for your presentation. I'm Chris Stoddart. I'm a reader in the Department of International Politics. I work on critical national infrastructure protection for Airbus. And I asked this question of my colleague, Dr. Kevin Jones, who works in this space. And I go to a lot of events where I see a lot of potential technical solutions to the issues you're describing. I asked this question to Kevin, so I'll ask it to you and you see how you feel about it. This came from Verizon, and it's a direct quote, and he said, you might say our findings boil down to one common theme, the human element. Despite advances in information security research and cyber detection solutions and tools, we continue to see many of the same errors we've known about for more than a decade now. How do you reconcile it? I'm sorry.
You are a little bit fast. I did not catch the question.
I'm so sorry. It's broadly this. There are an enormous amount of tools out there, including intrusion detection systems.
Yes.
There are a range of human factors sitting in and around this space. There's also issues of trusted insiders potentially going rogue. So how do your solutions fit in with that paradigm and framework? It's unlikely to capture everything. That's kind of what I'm getting at.
I did not catch exactly.
Well, the human factor. So whether insider threat is, did you monitor that also with your tools, or can you do that? I think
monitor the human factor. You
well,
mean?
that an insider is attacking your own system, like an insider of the company or the infrastructure you're monitoring. Can your tools, your 7 tools you mentioned, could one of them find that or detect that?
But by human factor, you mean someone who changes the structure, you mean change the values, someone who's working in the control room, who makes...
that potentially, yes.
Yes, this is, okay, this is an aspect which we see from the effect. I mean, if some change some values, and we detect these values are in a strange state compared to normal state, we can detect it. What, for instance, has happened in other systems, but this is more sophisticated attacks like Stuxnet, that you change some status and the SCADA system itself sends back values which are not the real ones. And this is detected, for instance, in our case for the PLC system, because this is something in the Stuxnet they've changed the PLC behavior, and so they, by our tool potentially detects this kind of attacks on PLC, so it may detect this kind of attacks, for instance. But I don't know, other kind of, the human factor is obviously something, depends in which part of the system you are attacking.
Yeah, but part of what I'm saying is it's the difficulties you've got in looking at it from a perimeter defense point of view. That if there are already barbarians within the gates, then you're not going to solve it by the solutions you're looking at. Okay. It's not so much a problem with your research, it's a wider conceptual problem, if you want to put it that way.
Yes, I agree with this. It's a conceptual problem, how to separate the human factors from the real operation, how they affect the real operation. This is, we don't face it specifically, we face it on the other side.
Thank you.
Any other? Yeah, here in front.
Hi. Yeah, thank you for your talk. It was very interesting. You raise alarms if something is not right, and some sort of operator has to react to these alarms. I think. How much data do you store? Can you go down or drill down to the event which caused the alarm?
Okay, so in the we have the graphical interface. I did not show it, But we have two users in the graphical interface. One is the operator, which is, I mean, the first people who sees the events. And usually the operator have a green, red event. So they have an event, say, okay, there is an alarm there, that IP, that PLC, something there. So the operator usually does not make deep inspections because there's not the capability. So this is the first user of our tool. And they have just a warning that something is happening. And another thing I said is ours is an introduction IDS, non-EPS. So we don't make any automatic reaction because these utilities don't want it. And the other one is instead the engineer. He can log in and he can see what events have caused the event. So he has capability to enter the database and see, okay, this alarm has been caused by this, and this event. So there is this possibility for the engineer to look what has been caused the alarm, what is the reason. And the question, how many events you mean? If you...
No, if you store the raw data, or if you just store there's an event.
Okay, take on that the tools have, as I told you before, are separate tools. So they make investigation on the packets level, process level separately. What they send to us are only the alarms, which have common format, which have a common protocol to have information, but not the wall why the packets has generated that event. This is something, there is a separate interface for each tool where you can examine it. But the global tool examines the global event. I mean, not the why the packets tool, for instance, has generated the event. This is in the single tool, which has obviously its own interface.
Okay, so you have no way to know if it's a false positive?
If it is a false, the problem of false positive is, okay, we have severity level. So if the packet tools tell me I have a warning very high, I must trust him. Because I said, okay, this is very high level, so probably the packet tool has said. If sends me an alarm which is low level, which is just an event not so high, I can decide. So I say, okay, this is an alarm, this is another event. Is correlated with other events? Okay, I raise a false an alarm. Otherwise not. This is why I reduce the false positive, because unless they are very high levels events, and probably the packets has detected something important, so I trust him.
Okay, thank you.
Yeah.
Well, thank you very much, Giorgio. Let me get this one here. Well, thank you. We have a little bit of candy for you to travel home. I hope it won't melt in Italy.
Yeah.
Well, here is the weather here is more supportive for candy and chocolate like that.
Thank
So thank you.
Thank you.
So next up will be Dr. Robert Koch. We have a really nice, as also last year, a very nice short paper in our proceedings from him. He will give a nice presentation of how we could actually protect wind power plants which are distributed and therefore are harder to protect than critical infrastructure which is gathered at one place. So the stage is yours to give us those answers.
Thank you very much, Raik. Dear ladies and gentlemen, I'm very happy to be here to talk a little bit about our current research project, which basically deals how to realize an intrusion detection system which can be applied to quite outdated systems where you're normally not able to backfit any security means. So the situation is well known. We are doing research in the area of intrusion detection for more than 35 years. So we have a numerous selection of systems out there, tons of scientific papers. But on the other hand, we see an increasing amount of net losses, increasing accidents, data accidents. So this graph on the right, that's from informationisbeautiful.net. And a few years ago, that was a very nice figure. So you can clearly see some data mistakes. But nowadays, we see all the time so many data leaks and trouble. So it's very crowded nowadays. So McAfee made a very interesting study in 2014. And of course, the dark figures are quite challenging to identify, but they estimated the loss based on cybercrime for 2014 to be approximately about 445 billion worldwide. So we can say maybe this year about 700, 800 billion, and Juniper made an estimation that it will come up to $2 trillion US up to 2019. So a lot of money is burned by that. Especially ransomware, for example, is a very successful business model for the cybercrime. If you have a look, for example, at CryptoWall in version 3, that single software version affected loss in total about 325 million US dollars. The typical ransomware we see nowadays is going to a desktop PC and encrypting your data, and you have to pay some money. And that's much more interesting if you can put such a ransomware into an industrial control system, because the average company will have much more money and interest to get back the data and the access to the system than maybe someone has privately at the desktop PC at home. So when you have to pay normally about half a Bitcoin something about $2,000 at the moment, half a Bitcoin or a Bitcoin to get your data back, we see this ransomware, nobody paid, but we see it out there, and the amount was 222 Bitcoins to get access to the system back, and that one was specifically for ICS systems, for the human-machine interface of an ICS system. So the endangerment is increasing for the ICS, of course, and we see a lot of other threats like terrorism, sabotage, espionage, and other things. If we take a look a little bit back, the bad security situation is well known, but for example, a report presented by the SANS Institute last year highlighted that even we know all the problems, the improvements in the security area are quite little. So a lot of the high priority concerns we identified quite a few years ago are as prevalent as ever. Another very interesting report was published by the US Department of Energy in January this year, and they highlight the imminent danger from cyber attacks to bring down the grid in the US. And of course, that's not only for the US, that also applies to the grid in the European Union. So what are the particularities of industrial control systems which make our life sometimes a little bit harder to implement intrusion detection and stuff like that? On the one hand, a lot of these systems are quite old, and back to the time when they were planned and designed, nobody thought about they will ever be connected to the internet. But for example, new business models, like having a look at you can deal with energy nowadays, they forced to connect these systems to the internet to realize these new business models. And of course, air-gapping a system is not security enough nowadays. Also, they have a long service life, 10 years, 20, maybe up to 40 years. And we recently saw the ransomware WannaCry affecting mainly Windows XP and Windows 7 systems. If you have a look out to the ICS systems which are running until now, today, you even can find Windows 3.1 dealing with critical infrastructure. So that's a big issue, and it's not so easy to update these systems from time to time. Then they have to function as specified under maximum load. So it's quite challenging to add additional processes for security afterwards, because they still must be able to provide the specification as it was in the beginning. And of course, patching has some real-world challenges. For example, you can see that in the ICS, but also, for example, with recent IoT devices, Internet of Things. Sometimes you know the vulnerability and you were able to patch it, but you can't patch it because, for example, you don't have enough memory in the system. So you are not able to close the security vulnerability even if you identified it. Further challenges certifications, especially with medical devices, and also on an increasing attack quality. Let's have a look at the attacks on the power grid in Ukraine in December 2015, and in the northern part of Kiev last December again. So some shortcomings of today's security systems we try to apply. Often they require access to the data. So looking into the data stream, into the connections, for example, to apply deep packet analysis, and that limits the opportunities to put that into the system. Typically, an integration is required, and because of the mentioned reasons, that's often not possible. Also, there's quite a delta between the detection capabilities in theory and the stuff you really can realize in real world. Cost can be another aspect. If you have $10,000 or $100,000 per intrusion detection system and a very complex system structure, it can be quite expensive to realize that. And a very important aspect we shouldn't forget is that also a security system, maybe it's based on hardware, but at least it has some code. It's programmed. And by that, it brings in additional security weaknesses, because the number of security weaknesses in a code is based on the programming model and the quality management you are doing and the code reviews and everything, and also based on the programming language you use. Based on that, you have a number of vulnerabilities with your security product bringing into your environment. And for example, Tavis Omandi from Google demonstrated very impressively the past years how many badly programmed security products are out there. So the requirements for our system were identify a system that can be used to secure the target system without an integration into the target environment. So no sensory that has to be installed in the ICS itself, no code that has to be added or something like that. Usable in complex environments, so it should be scalable and quite cheap. A quite tamper-resistant measurement technique, we will see that. And of course, you want to have high detection and low false alarm rates. So our system specifically targets ICS systems. And what Mr. Langner in his very nice presentation told in the morning, that's exactly happening here. We have here an environment with a quite low entropy of the elements. And that's why this technique is possible and working. So we have a quite limited number of processes running in an ICS, and we can very well identify these processes and their characteristics. So we are able to find the ground truth of the whole system. We are using the current reign of the electronics to do our evaluation and detect anomalous behavior. The basic detection method is behavior-based. So looking, okay, what is different than, for example, yesterday, what is an anomaly? But we supplement that by knowledge-based aspects. So we identified different voltage patterns which only appear when you can see an attack. So to improve the detection quality. This is the basic setup we used in the lab. Not going too much into the detail, because it was the aim to use some very cheap hardware. We built a measurement setup based on a mini computer, an Android device. And in the beginning, we had to identify, is that device good enough? Is it able to do the measurement process? So we also used some multimeters and some high-performance PCI cards with very exact measurements to compare it. Is it the right way? Is it working? So only a few ideas about the architecture. The main core of the system is a Odroid U3 mini computer, so that costs about $40, quite cheap device. It has a very nice extension. It's called Odroid I/O Shield, which adds about 36 additional ports, so we can add more measuring electronics via the I/O Shield. We integrated it to be compatible with the well-known intrusion detection systems Nord. So if you already have some snort system running and doing a knowledge-based analysis of the data, you can correlate the data with our system, but that's not necessary. And we also adapted Snorby, the well-known interface, for the visualization. I will show a picture a little bit later. So some challenges during the development. If you have a look at the power consumption of the computer itself, we saw some interesting influence of the switching power supply. So the power supply produces 5 volt of direct current, but if you have a close look to the direct current, it's not really a continuous wave, but it's a kind of sawtooth. So the power supply switches on, produces some energy, then switches off, and that very fast. So in the end, you have this 5 voltage direct current, but in real world, it looks like that. We'll come to that back later. Another very interesting aspect, of course, is the heat dependency of the power consumption. So if the processor is heated up during operation, the power consumption goes back, and you have to take that into account. But the more challenging part is, of course, if the circuits heat up, you have to cool them, otherwise they would be destroyed. So if you have an active element, like a fan, it's normally steered by the temperature, and the returns per minute of the fan are adapted to the temperature of the circuit. So at that point, we are introducing some quite awful differential equations we have to solve. So in the beginning, to make the development of the product a little bit easier, we changed that active solution to that passive one to ease up that problem, and that's further work. One interesting aspect, very important, is finding the correct sampling rate. As I told, we want to use quite cheap hardware, so we can distribute it with no big pain. So it is good to have a quite low sampling rate. So in the left picture, you can see a measurement which was produced by 10 Hertz sampling rate. And you can identify the flank where the process started, and then some pattern. And here at that point, the running process was finished. So you have the basic idea of what is measured. The second picture is with 50 Hertz. Here you already have a quite better picture of what is going on, the steep flanks and very clearly identifiable beginning and ending of the process. And if you further increase that in the third picture, then additional information is added, but not about the process which is measured itself. Here, in that picture, you see from the switching power supply, the on and off switching of the power supply itself. And that is noise. We don't want to have that. So having a too good sampling rate is even bad in our case, and that's fine. So in the end, we find out that using a sampling rate of 10 Hertz is enough. And that's fine, because you can provide it with quite cheap hardware. This is one example about a pattern we identified. So during a SSH brute force attack seen on the targeted device, this is the kind of power which is used by the circuit suffering from the attack. So a kind of triangles and a very specific pattern. So this is one of the patterns we integrated to improve the quality of the detection process itself. Having a look at the detection rates in the end, there's some nice story behind that. When my students did the evaluation, they give me a phone call. I think it was a Friday night about midnight. And they were quite panicking. And they started the phone call with, "We have a very big problem. The values are too good." And that's because of a reason. I'm giving lectures for intrusion detection systems. And when you have a behavior-based detection and you see 100%, then something normally is going wrong. For example, if you're using neural networks for the detection process, and you have 100% of detection rate, then the network is overfitted. That means that in the test case, in the test scenario, it functions very, very well, and when we take it and put it out to the real world, the detection rates drop down dramatically, so not usable. We discussed a lot about that, did additional measurements, and finally, yeah, we really had in that case 100% detection rate, but that's really based on the very simple environment we have. A low entropy environment like ICS. If you put such a system to a full-blown desktop, your home PC or something like that, that's not possible. So that's only because we have a very, very clear defined environment with the industrial control systems. The false alarm rates are also quite nice, very close, very little, and a new aspect which is not able to be provided by current systems is a classification, because only having the anomaly-based detection doesn't allow you to classify the event, only to say it's good or it's bad. And the patterns we introduced, like the SSH brute force attack you've seen, that enables us to say, okay, which kind of attack is it? That's not working too good, so about 45% in average, we were able to identify also what's really happening in the background. This is a shortcut of the Snorby website. So we added this new option about energy severity, where you can have a look, okay, there's an alarm raised based on the current drain misuse. So a possible scenario would be, for example, in a wind park, where you can add such a detection electronic, such a measurement, to every of the wind power engines, and collect that together to a central picture. So one example for the distributed setup types, they're described a little bit closer in the paper, not going too much into the details here. The main difference is the quality and the precision of the identification where the attack happened. So like for the question coming from here, you can collect about 36 different sensors with one Dr. Watson, so we call our system Dr. Watson. But when an attack happens, you can only say, okay, within these 36 devices the attack has happened, but not specifically saying, okay, it was that device. So if you need this level of detail, then you have to add one measuring electronic and one Dr. Watson to each specific area you are looking for. But yeah, depending on the complexity of the system, because we use quite cheap components with about $40, that's realizable. And in the end, you can collect the pictures that's scaling very well, for example, in your headquarters to build up a situational awareness picture. So to summarize it, our proof of concept, our Dr. Watson, is an intrusion detection system which is using the current drain, the evaluation of the current drain, to identify attacks on, for example, ICS systems, SCADA systems, and which doesn't need any integration. So you can realize that completely contactless, for example, using Hall sensory to get the energy values. So you can add it to also very old ICS systems and increase the security of these systems by that way. It's quite scalable and very cost efficient, of course, and the detection rates and the false alarm rates are very well. So the next steps really would be to put that system into a real-world system, ICS system, to identify, okay, how good will then be the detection values. But we have a very good mood for that because of the good working performance at the moment. And also the Odroid U3 we used is not produced any longer. There's a newer version of the mini computer to the same price, also $40, and it has additional capabilities. So we are reprogramming the code, for example, using the graphical processor for the pattern processing to improve the detection process and the quality itself. Some other aspects I already mentioned. For example, we will have a look how to deal with the temperature-based aspects, especially when active elements like fans are introduced. So that's a little bit more mass, and the calculation is more easy with a newer and more powerful hardware of that. So that is basically a quite fast overview of our intrusion detection system. Do you have any questions?
First of all, thank you, Robert. And then the question from the young gentleman back there.
Hi, my name is Stefan Riegler. I'm a PhD candidate at the Hardware Security Lab at TU Vienna. And so you're using Dr. Watson for power analysis as an IDS. And thank you for mentioning that your security products may introduce security vulnerabilities. We had that in the past many times. And so what about using Dr. Watson as a differential power analysis as side channel attacks for the ICS so that you can extract the keys? Do you think about that?
A very nice question. So, because it's completely isolated from the rest of the system, it's not easy really to manipulate it or to attack the system itself. And we have a nice feature. I was not going into the details with that. We have a nice feature. We are not only watching the power consumption of the target environment, but also of our system itself. So it has a self-monitoring capability for all its processes, trying to identify if someone is manipulating the system itself. So in theory, of course, you can try to attack the system, especially if you are forced to network it with other systems and going onto that by that way, but it's an additional security layer, completely isolated from the original one, so no additional attack vector in your real target, but completely separated. And based on the self-monitoring capabilities, I think it's quite challenging to attack it. I would not say it's impossible, but it's quite challenging.
Thank you. Any other questions? None? Well, I have one or two for you. Sorry. Well, we're talking about wind power plants. So they don't produce always the same amount of power. How does it influence the system? Does it influence the system at all?
In theory, it could be possible that some instability in the power may affect the measurements, but we haven't seen that yet. So what we have seen, the energy is all the way good enough not to produce any bad results, and that may be also because of the quite low sampling rate of 10 Hertz, because a lot of crap we don't want to see can be filtered out by that way.
Okay. And another one would be, if I'm thinking about the attacker knows that you're using Dr. Watson and might have seen this presentation today, what is if somebody tries to actually fake such a pattern as you know it's non-malicious, and would you be able to detect it still, or is it will be a hard case?
Very interesting question. So in theory, you may be able to identify the banning behavior of the controlled environment. That's not really difficult. You can do that. And then trying to build an attack based on using only program code that exactly reproduces the energy consumption of a real world or of a banning process. But the challenge is that you have to run these code even on top of the system. So it will definitely add some more energy consumption than without it. So maybe it would be possible for a very, very sophisticated attacker. Let's talk about nation states, but definitely not for the average attacker.
Okay, so your students can try that. Well, the sample rate would at least go underneath 100% then in this case. Okay, well, thank you very much. We have also for you some candy.
Thank you.
This time you don't need to grow your own plants. This time you can directly start eating.
I'm still using the device.
Okay, great. For all of you who haven't attended, we had a click and grow last year, and you're hopefully growing some plants by now. Okay, thank you very much. Yes, so the next one up is Mr. Trevor Goldman. So when I heard what he's going to talk about, I was directly like asking myself, will he try to say? Because it was something about Internet of Things and industrial control systems. So I was like thinking, how does that fit together? But we're gonna hopefully find out how it fits together and how it could work together in the future. The stage is yours.
Just give me a few seconds while I try and find my glasses here. All right. First of all, thank you everyone for coming to the presentation today, and thank you for the organizers for having us, having Waterfall Security. Waterfall is a technology company. We are focused on protecting the safety and the reliability of industrial networks. We feel that without proper cybersecurity, there is no protection, there is no safety, there is no reliability for industrial networks. Now, before I go any further, I was giving a presentation in Japan a couple months ago. They said I had 20 minutes. What they forgot to tell me was that in that 20 minutes, there was going to be a translator that would translate every line or, every couple lines. So 20 minutes, no translator?
I won't translate anything.
All right. Just to confirm that, give me a second while I get my notes proper here. So, what I'm going to talk about is the industrial Internet of Things related to the outsourced security model that we had a test in Hannover Messe at the conference several weeks ago. Then I'm going to talk about the actual technology that we used in that test bed, and I'll open it up for questions after that. So, which one? That's next. First, what I'd like you to think about while I go through my presentation are the two challenges that we have. We have the cyber security challenge. Security challenge says that all software can be hacked and all attacks are information. Any message can contain attack information, and universal connectivity dramatically increases the attack surface. Cybersecurity. Then we have the interoperability challenges. Anybody that works in the industrial environment knows this. Industrial protocols and applications are not friendly or cloud friendly, and they probably will never be. So there are few standards for what industrial data should look like or what this data should mean. So keep these two challenges in mind as I go through my presentation. So the industrial Internet of Things. Before we go on to this, let's back up to the Internet of Things. We all know what the Internet of Things, it's making dumb devices smart. We've got our lights, we have our cameras, we've got, I hear there's toasters now. I don't know why you'd want a toaster connected, but we have toasters connected where you can now make your life easier. You can program it remotely. I have, unfortunately, I've got these LED light bulbs at home called LifeX, if anybody's heard of those. I think they're amazing. I changed the colors. It drives my family nuts, but that's the Internet of Things. The industrial Internet of Things says that everything is going to get easier on our industry. It's going to have remote monitoring, remote control, remote management, remote reprogramming of our devices, and of course, the all-important big data analytics. Problem is that everything gets easier for us. We're also making everything easier for our attackers. Let's talk about the actual vision for the industrial Internet of Things. The vision is pretty much one of universal connectivity and interoperability. We all know the network is flat, everything's connected, and everything is on the internet. Physical components such as valves, pumps, and even catalytic crackers, they're all standard. For all these standard hardware, we have standard sensors, standard control loops, and standard intelligent devices. All of these APIs are open and they're all interoperable. So we operate these things remotely. Our operators, our engineers, our managers, all of our experts are in their headquarters, and everything just works. Fantastic. Here's an example. We have a physical process we have in our industry, and we want to make it better, or there's a problem. So we all go down to our local distributor. I'm sure we've got one down the street. I know I've got one next door to my house. And we install all of these, let's say 100 widgets onto our physical process. And what happens is they all auto-connect to the vendor's cloud via the internet access, the cell network that comes attached to these devices. And then these widgets, they're going to discover each other. They're going to consult the vendor, and they're going to see what's around them, what they can do to realize this overall, what they can do to, find my place here, what they can do to find out the context that they're in. Thank you. Once they figured out this problem, the opportunity to discover and to find out what the problem is now complete, and they connect onto a remote HMI, and again, everything just works. The problem's fixed, or the actual optimization is realized, and of course, it's secure. I mean, it has to be secure. They've got wonderful buzzwords such as trusted platform module. Wow. Root of trust, trusted hypervisor, fine-grained, least privilege, role-based privilege. It's also clever. None of this is a secret to those that work in the industrial security environment, or any of our security experts like you guys that we have here. The Industrial Internet Consortium came out with a document last September talking about just this, that the problem for putting any of our devices or any of our information onto the cloud are interoperability and security. So this isn't a secret. What this document also talks about, and I really recommend that everybody has a look at this document if you haven't already, is that we must also talk about the perimeter. The perimeter is important. Now, I understand that on the IT side, they say, well, Trevor, the perimeter's dead. How do I put a perimeter around your cell phone? You're taking your cell phone back and forth from home, your laptop that you go home with. How do I put a perimeter around that USB stick that's in your pocket? Well, those are all great questions, but really on the OT side, it's the wrong way of looking at things. And I'll tell you why. When you're on the OT environment, and you get up to, and those of you who are in the military will understand this as well, when you get up into onto an industrial site, what's the first thing that you see is you get to a gate. You get to a gate where you're going to talk to a guard, a physical perimeter, physical barrier. Then you're going to get into probably a hut or into the building where you're going to get another barrier. They're going to ensure who you are, they're going to see you, they're going to look at your ID, enter a key code, get further and further inside until eventually you're at your workstation, enter a password, and then you're inside, able to do whatever you're allowed to do. All of these are physical barriers. Wherever you have a physical barrier, you have to have some sort of cyber security perimeter as well, and that's key. All right, so enough of the industrial Internet of Things. Let's have a look at what happened in Hanover Messe a few weeks ago. I'm going to go back to my notes because my notes weren't able to go on to there, if you excuse me. By the way, my colleagues at Waterfall, they kind of make fun of me because I have a habit of apologizing. So what I'm going to do now is I'm going to apologize for apologizing. It's in my Canadian nature. I'm sorry, I can't help it. You see? All right. So the Industrial Internet Consortium and the joint demo happened in Hanover Messe 6 weeks ago. I'm not sure, was anybody able to attend the Hanover Messe at all? Anybody here? I don't see any hands, so I'll take that as a no. So we joined 24 vendors from the IIC and the Industry 4.0, demonstrating secure cloud connectivity. What we did was we showed that strong encryption can be at the heart of outsourced security demo with our Cloud Connect, the technology right in the middle. And I'll show you some slides later on exactly what we did for that. We illustrated how to benefit from direct integration of the control systems with the cloud system without any risk of any remote online attacks coming back and damaging the industrial systems, and that's key. All of this we did by proving that the IIC and the I 4.0 members can and are able to work together. And believe me, it wasn't easy. There's a lot of distrust amongst a lot of these vendors. The outsourced security concept is very timely. There's a lot of vendors that are coming out here now that are wanting to do this. So here's why. Here's the whole concept. Many industrial sites want intrusion detection. Unfortunately, they don't have the means to develop their own in-house expertise to interpret complex alerts and other information. So in other words, they have no idea how much trouble they're in intrusion-wise. So they need to outsource it. Solution that a lot of companies are doing is they want to adopt the outsource real-time security monitoring to either an IT or a cloud-based third-party SIM or SOC. The vendors spent several months, and again, there was a lot of teeth pulling getting this to go together. Well, 24 of these vendors, you can imagine a lot of egos and a lot of companies saying they're better than the other. But what happened was that this was the first large-scale demonstration of its kind ever. The goal was to show secure interoperability as possible amongst many vendors and many consortiums using different routes of trust that control all of the encrypted communication. So let's have a look how. Now, unfortunately, I was, well, first of all, had I put the real schematic up there, it was a little messy, so I was actually forced to put something a little more basic on there, but you're going to get the whole idea of what the topology was with the wiring. So what we have over here is on the left-hand side, your left, on the IIC pavilion, there were several of the vendors down there, and if you're interested in who was actually involved in this, I can show you the real schematic. We can talk about who the vendors were. So we had the IIC vendors that were connecting through the firewall so they couldn't get back to each other, again, the egos and everything else, where they went through the technology, the unidirectional gateway or the Cloud Connect, and then going on to the SIM. So let's have a look exactly how they did that. Once again, the Cloud Connect was at the center of that. That's in the blue. Each of the vendors were able to reliably integrate their industrial Internet of Things devices, as I said, through the gateway to their SIMs that were on site in each one of the pavilions, or also onto the internet, onto a cloud-based device. So what they did was each vendor connected using encrypted TLS TCP v3, so version 3 syslog streams. The Cloud Connect then aggregated those streams. So that is Cloud Connect, that's the technology you see in the blue. As I said, it aggregated the streams and sent a copy of each of these streams to each of the cloud-based or the locally based SIMs. Once again, with the technology, they were 100% assured that no attack could flow back into the industrial devices. As I said, this was very simplistic schematic. Over here on the left-hand side, there was actually an off-site vendor who was sending industrial Internet of Things information streams through another gateway that simulated an off-site going forward. Once again, I'll be more than happy to show everybody how this works or what the actual schematic was if you're interested. So, here's the technology. The technology is a unidirectional gateway or Cloud Connect. There are differences in the two, but Here is an image of the unidirectional security gateway, the technology. The technology consists of hardware and software. Everything that you see in the color in the red or in the orange is the unidirectional gateway. I like the talk about the hardware first because for me that's where the magic happens. So we'll start with the hardware. You see you have a TX module, a transmit module that has a laser but no photocell. So it's physically only able to send light. Then on the other side we have an RX or a receive module that has a photocell but no laser. So physically it can only receive the light. These are connected by a short fiber optic cable. Once again, 100% assurance that information will flow in one direction only. So we have the security, now we need to move the data. We move the data by having a computer on either side of the hardware. The computer, the TX agent, as you see there, is the waterfall or the technology software that collects whatever it is that you'd like to put on the other side. So for example, you have OPC, all the industrial protocols, OPC, Modbus, ICCP, DMP3, or syslog streams in our case. Once it takes the data and sends it through the unidirectional or through the hardware, it will put an exact replica on what you see here as the RX agent. Now with an exact replica on the RX agent, that will then forward it to the replica server. So people that want to get the information, let's give a live example of SQL Server. SQL Server on the industrial side can be OSI Soft Pi, it can be anything, but we'll start with SQL Server. SQL Server on the TX agent will collect as a user all of the changes, send them through the hardware over onto the other side where there's now an exact replica on what we have there as the corporate network. So now people that want to collect the data or they want to do queries, ad hoc queries or whatever, they can do those from the replica server. And they're going to get the exact same answers as if they were asking for it on the industrial system. With this, if something happens on the corporate side, an attacker, ransomware, anything like that, of course it's bad. We have steps in place to be able to deal with this. IT will come in, they'll isolate it, they'll recover everything from backups, and 3 hours later, they'll have everything up and working. While all of this chaos is taking place, the industrial network, the physical process that you're protecting will just continue to work. It will continue to produce whatever it's producing. In other words, it's completely oblivious to anything happening on the corporate side. Now, if we talk about the, since we brought it up somewhere, the attack on the Ukraine a year and a half ago, even if something had, the malware had been put onto the industrial network, had they had the unidirectional gateway in place, there would not have been a method of controlling that malware, so there would have been no method to remotely attack, remotely control, remotely shut down any of these critical networks. And that's key. We have to make sure that information can flow in the direction that we want it. In other words, from the industrial to the corporate and never the other way around. All right. What time did I start? Do you know? Do you remember? What time did I start?
Go on.
I know I got lots of time. I'm just, you know.
Yes, yes.
Here you have an example going back to the Hanover Messe where you have, I have 3 examples of what we did with the schematics where here we had several vendors that were creating their industrial Internet of Things streams, sending them through the technology, the unidirectional gateway, onto local SIMs. And the next one we have the SIMs, as I talked about, sort of the industrial sites that were creating their data, their industrial Internet of Things streams from a cloud outside of the pavilion, sending it inside where the streams were aggregated, and then sent through the unidirectional gateway into the local SIMs. And something similar from the IIC Pavilion. I'll just leave that up for a second. If you'll allow me, I'd like to just talk about Waterfall for a second. Waterfall, as I said, is a technology company. We've been established for over 10 years now. You don't have to do that. I know what my notes are. It's fine. Thanks. We've been around for over 10 years now, and we have installations all over the world, including APAC, Asia, Europe, North America. We're installed in several of the power plants, including nuclear power. In fact, in America, we're installed in over 60% of the power plants there. I'd like to leave you with this. I forgot my books. Can you just pass me my book there, please? I have several copies of this book written by our industrial guru, our vice president of industrial security, Andrew Ginter, for those of you who don't know him, based out of Calgary. And he talks about the 3 laws of SCADA security. Number 1, nothing is secure. Number 2, all software can be hacked. And finally, all attacks are information, and every bit of information can be an attack. I'd like to just clarify on that one. If you have a safety system that is connected to your environment, and that safety system is protected by a binary 0, and somebody sends a binary 1, that's an attack. So remember that in a connected world, our enemies can attack our systems. Well, I'm from Vancouver originally, so I like to say, well, sipping coffee in Vancouver, controlling our networks, and that's what we need to stop. And with that, I want to thank everybody for your time and your attention, and I'll open it up for questions.
Thank you. I see 2. First,
I can't see anything, so if somebody has their hand up, I will. You go
will,
ahead.
You will hear it.
Yeah, I'll hear it.
I saw 2 questions at least.
Kim Westerlund, hi. I will hear.
Okay, there you are. Thank you.
Excuse me for the simple question, but how does this differ from traditional data?
You're going to say data diode, aren't you?
Yeah.
All right, good. Thank you very much. And one of the things that I didn't want to put on is I didn't want to make it a whole commercial about the waterfall technology. And that is a really great question, because you do have, if I put into it, and I can't say this, nobody can tell my CEO I use the word data diode, but it is kind of that technology in the center. What differentiates us is our ability to take over 100 different industrial protocols and send them through the hardware itself. So we deal with OPC, OSI soft PI, as I've mentioned, DNP3, all of the file and folders, and we do these all without any reverse engineering. In other words, we do it all in real time. We take the data, we use the APIs, the STKs, and we work with these companies. We actually have strategic partnerships with several of these companies where they have us in their testbed, and they will continue to work, or they will continue to support their product after after we have been having troubles without saying the company, sorry, without having the technology installed. Or they'll continue to support the product after we've been installed in their site, is what I'm trying to say.
Hi, Brad Bigelow from Shape. I guess a question with 2 parts to it. First of all, I mean, it is basically a data diode. So that's wonderful, but I mean, a lot of these protocols, the reason people remotely monitor isn't just to remotely monitor, it's very often to remotely monitor and control, and many of these protocols are in fact not one-dimensional, they're bilateral protocols. I know certainly the IP stack struggles to deal with data diodes because very often the protocols expect to have some sort of response from the high side or from the trusted side. But as you showed your kind of high-level view of the system, what you see on the plant side is I assume it's your SIMs, right?
No, these were all third-party SIMs. So
in any case, your monitoring ability is dependent upon the ability of those in-plant resident SIMs, right? In other words, those SIMs are passing information up to you. Is that true?
well, no, perhaps I didn't explain this properly. I'll go back to my notes and see if I can just find the place there. And I'll just try this again, just really quickly.
Just go to the slide that you had with the...
Yeah, I was trying to go back there, and I'll also get the notes, see if I missed a point here. Can we get the slides back up?
Well,
there we go.
You can't. You've got a piece, I guess what my point is, yeah, no, I think it's the one after this.
No, that's ours. Or I see what you're saying, so
Yeah,
here,
yeah,
right.
yeah,
Okay, yep.
Okay, so you have the end system and you have the local SIMs.
Yep.
I guess part of it is you may have a technical integrity of the system, but you still have the possibility of an insider-introduced vulnerability, right?
Maybe I'm not explaining it properly. I'll try this again. What we had over here where it says end system,
Right.
that's actually, those two were in the pavilions. They were in the pavilions. They were simulating, creating their industrial Internet of Things streams, their syslog streams. Those streams were sent through the Unidirectional Security Gateway, or the Cloud Connect, into another part afterwards, in other words, on the IT side, local SIMs. And we had SICK AG, we had Simmons, we had McAfee, Intel, several of the vendors that were working on those. And the thing was that when these streams were actually aggregated on the right-hand side, they were aggregated to everybody, so everybody had the ability to read these.
Right, but they're going to have to stay current with essentially the evolution of the systems on the monitored side, right?
So, how current are our OT environments?
I understand, but the whole...
That sounded argumentative, and I didn't mean to.
Yeah, because
right.
of vendors wanting to connect into their in-plant systems
right.
for remote monitoring control and remote patching, right?
Right. Well,
okay.
We're talking...
So you're in effect cutting that link, still creating the necessity to go out and locally, physically install patches at the industrial facilities. I mean, that's the downside of this, which is in fact kind of counter to the business model of why a lot of people are going to remote monitoring. And my second question is this: if you're doing this in nuclear power plants,
yep.
I'm just curious about what the nature of your contract is as a service provider, given that the magnitude of the liability in the event of a catastrophe in that sort of situation. There's no way your company can bear that liability, as some of your clients are essentially industrial, publicly insured kinds of arrangements. It seems to me that's one of the downsides is, in the end, there's no way you can take on the liability that goes back to the original systems, the owners of the systems that you're monitoring.
Right. First of all, we're not a service provider. We're not, we are a software, we're off-the-shelf provider. We give the hardware and the software to the company, wherever it is, let's say to the nuclear plant, and they install it, and it sits there and does what it does. As far as any liability or anything like that, that's not going to change. We essentially want to protect their perimeter, whether it's from the IT to the OT, or the OT to the IT, or whatever the perimeter is on that side. And I'd love to talk to you about this offline and give you a much better explanation on that if I could. I didn't see if you nodded there, but I'm hoping you did. Yeah, okay.
So any other questions? Yep, the gentleman back there.
Lauri Gorspan from CDI NEC. So I have a question which maybe reiterates the last one a little bit. What do you see as the most effective defense against the attacks against the sneaker net? Basically, the people who are...
You're talking sneaker net?
Yeah.
Right. So I also have, through Andrew Ginter, there's a, if you want to look on, I think there's a, where is it? Somewhere on the net, where he does a demonstration about the 13 methods of breaking through a firewall. And of those, he does talk about the sneaker net. And as I said, we are protecting the perimeter. There always has to be a physical perimeter where there's a cyber perimeter. As I go backwards to what I said earlier, you're still going to have that perimeter that you need. You're still going to have your secondary security devices, intrusion detection systems inside, ensuring that you can still secure the inside to prevent these sneaker nets. Because let's face it, somebody comes in and takes the unidirectional gateway or even takes the firewall and smashes it, well, they're probably going to do a lot more damage as they go through. If that answers your question.
So one last question for me.
Sure.
How do you actually ensure that if you have the data coming from your, not air-gapped system, but like your industrial control system, that is actually replicated to your actual network? How do you ensure that you know that it was replicated?
You're right. So when we send the data, because it's the data dialed or unidirectional gateway, if you will, when we send the information, we're sending it blindly. What we've done, because we've been doing this for over 10 years, is we put different pieces of information with these data that we're sending through the gateway so that when it gets to the other side, we have checksums. We have packet numbering, so if 1, 2, and 4 comes through, you know 3 is missing, you have to go on to the other side, press a button, and have the other packets sent through so you have a full piece of data. And there's other monitoring things, SNMP, SMTP, syslog, and things like that, where you can ensure that you have a timely information to discover if there's a problem.
All right, thank you very much, Trevor. We also have for you some chocolate to take home with.
Yeah, that's going to melt.
Well, then you need to eat it in Tallinn. I think we have enough people to
I think we have enough people here that will help me eat this. So,
thank you.
Thank you.